Hi class. So today we're going to do some practice analyzing circuits for network and combination circuits. So I just made up a circuit right here. We're going to call this example 1. So we have a 9-volt battery coming into this combination circuit. So let's take a look at what we can do to simplify the circuit here. So these two things on the very bottom, it's a good idea to always start towards the end of the circuit. So I'm going to start with this one down here. As you can see, these two are in parallel with each other. See the junction right here? So that means you have more than one conducting path. So the current can go this way. I'm going to trace the current this way, it can go up, and the other part can go down. So you have two conducting paths. So I'm going to take the equivalent resistance of these two. So this will be 20 exponent -1 plus 30 exponent -1. And then you're going to take the inverse of that as well. So we're going to go 20 exponent -1 plus 30 exponent -1. And then inverse that one more time. And you have 12 ohms for that equivalent resistance. And then I'm going to take a look at these two. These are again parallel with each other. So I'm going to take the equivalent resistance of those two parallel circuits. So 10 -1 plus 10 -1 and inverse that. And we get 10 exponent -1 plus 10 exponent -1. Inverse that one more time and you have 5 ohms of equivalent resistance. So we basically have simplified this circuit like this. Just going to show you what it looks like now. So we have this, which is 5 ohm, and it is now this 12 ohm right here is now one resistance of 12 ohm right here. So there's a 12 ohms and there's the 5 ohms right here, and you still have the 5 ohms and the 50 ohm on this side. So now we could actually combine this one more time. So on the bottom you have these two are in parallel with each other. So the equivalent resistance for this is 5 inverse plus 12 inverse. Inverse that one more time and you have 3.5 ohms. I should have been taking 2 decimal place here. That's okay. We're focusing on the technique. So now we have simplified this into, you still have your 5 there and the 50 on this side. And now you have a 3.5 ohm on the bottom. So now you have one circuit with 3 series circuit. And so we can just combine all of them. So you have 50 plus 3.5 plus 5. So that will give you a total resistance of 58.5 ohms. Now it's very important that you get the total resistance correctly, as your calculation for the current and the individual voltages will depend on this. So that is our total resistance. So now let's take a look at what about the total current. So we know the total voltage is 9 volts. So I can use Ohm's law for this. I is equal to VT over RT. Total volts 9 divided by 58.5 ohms, and we have 0.15 amps of total current running to this. Now let's go back to the simplified diagram here. You know that the R1, so right now we can be certain that I1 right here is going to receive exactly the same current as the total current because it is in series with the battery. The same with this 50 ohm. We call this one R6. So this will be I6. And this is as well going to get 0.15 amps of current. Now we know that this whole thing here is going to receive 0.15 amps of current as well, but that will be the entire circuit that are in parallel with each other down below here. So what do they have in common? These two in parallel are going to receive the exact same voltage as whatever is running through here. So we can now calculate the individual voltages first and then go back and calculate the individual current and finish that off. So I'm going to go jump to, call this C, and because we now have the I1, R1 is given, and I6 we have, and R6 is given, we can then calculate the individual voltages that are running through those R1 and R6. So I'll go V1 is equal to I1 R1. So our I is 0.15 amps times resistance is 5 ohms. And this is going to get 0.77 volts. So that is our volts for the first resistor. And our V2 is I2R2. We don't have the V2 yet, but what we have is the V6. So we don't have to do this in order. We have to do it according to what we know based on Kirchhoff's rules. So we have V6, I6, R6. I6 is 0.15 amps as well. And the R6 has 50 ohms of resistance. So 0.15 times 50 is 7.5 volts. So this is receiving a lot more voltage than the R1, which makes sense to be about 10 times more because 5 ohms for this, and this is 50 ohms. So it's a higher resistance. It needs more potential difference. It needs more kick for the electrons to get through it. Okay, so we have the V1 and the V6. For this total here, we can figure out the voltage because together these two is 8.27 already. So this is 8.27 volts combined, which means that this combined resistance here is going to receive whatever the difference is. So this will be 9 volts. Take away 8.27 volts, and it's going to get 0.73 volts each. So now we know the voltage that's going to go through all of them for this whole thing. So we know the current that's running through it, and we know the total voltage that's running through it. I'm going to go to the second simplified resistance right here. So let's just write down what we have. So this is I1. We know I1 is 0.15 amps. We know I6 is also 0.15 amps. We have now figured out the V1 is 0.77. So we know the V6 as well. So those are done. We can figure out these two things that are in parallel with each other. The voltage that is getting through this simplified resistance is 0.73 volts. So that means that this is going to be 0.73 volts, and this is receiving 0.73 volts as well because they are in parallel. So we can write down this is 0.73 volts. That means we can go back to the original diagram. These two are in parallel. Know that V4 is also 0.73 volts, and a V5 is also receiving 0.73 volts. So now we know those, and as well as V2 is also receiving 0.73 volts, as well as V3. 0.73 volts. Because they are in parallel, we know that the total voltage is going to equal the individual voltage in each of the loads or the resistor. So we know the voltage individual. We can now calculate the individual current in each of these. So to calculate the I4, we go V4 divided by R4. So V4 is 0.73 divided by R4 is 20 ohms. And this is going to give us 0.05 amps. That's our I4. I5 is V5 divided by R5. Okay, so V5 is 0.73. Divide that by R5, which is 30 ohms. And this is 0.024 volts. Calculating the V2. So I2 is V2 divided by R2. So V2 is 0.73 volts divided by R2 is 10. And this is 0.073 volts. And lastly, the I3 is V3 over R3. The V is 0.73 volts divided by R3 is 10. And you get, again, 0.073 amps. And I wrote down volts here. So this should be amps for the current. Okay. Now, just to double check our answers, since we know the total current running through the entire circuit is 0.15 amperes of current. Okay, this is the total current running through the entire circuit. When you combine the current that is running through all the parallel circuits, it should equal 0.15. So just to double check, you have go back to the original diagram that you have. This R4 and R5 are in parallel. They should be receiving a total of 0.15 amps of current. So let's add the I4 and I5. I4 and I5 is 0.05 plus 0.73. And you get between these two is 0.78. And then you combine that with the 0.073 plus 0.073. And you get 0.146 amps of current. So rounding it off, you get 0.15 amps. So when you add all these currents here in I4, I5, I2, and I3, all these are receiving 0.15 amps, just as predicted using Kirchhoff's rules. So we have done everything here for our circuit analysis. Just to summarize what we have found, we found the total resistance, we found the total current, we know the total volts is 9 volts, we have found the individual currents, we have I1, I2, I3, I4, I5, and I6. We have the individual voltages, V1, V2, V3, V4, V5, and V6. The easiest one is to calculate the power. So to get the power is IV. So you can just calculate the I of each one times V. And if you were to look at the total power that is going through the entire circuit, you could also take the total current times the total voltage. And I'm just going to take that. Total current is 0.15. Multiply that by 9 volts of total potential difference. And we have 1.35 watts of total power. So I'm just going to write down the total power here. And the individual power is easy enough to calculate. So P1 is 0.15 times V1, which is 0.77, and you get 0.116 watts. P2 is equal to I2 which is I2. Where's our I2 here? 0.073 times V2, which is 0.073. So IV, and you get 0.053 watts of power. P3 is equal to I3, which is 0.073 times V3 of 0.73, which is also 0.053 watts. P4 is 0.05 times 0.73 is 0.037 watts. P5 is equal to 0.024 of I5 times 0.73 is 0.018 watts. And lastly, P6 is equal to I6, which is 0.15 times V6 of 7.5, and you get 1.125 watts. If you add up all the individual power in each of the resistors, you will get 1.35 watts of resistance, which is not very much, but then you also have a small potential difference here and a small current. So this is the circuit analysis for that circuit, which is a combination circuit.